Hello everyone. I want to introduce conditional probability. Now let's consider the roll of the dice. Here's a classic dice roll chart with every possible roll of the 36 rolls. Now I'm going to roll the dice, and while I'm thinking about rolling the dice, I want to ask what's the probability that the sum of my dice is at least a 9. But during the process of me rolling the dice, one of them slips away, and you notice that it lands a 6. Now will that affect the probability? Well, basically it comes down to this. I'm going to roll the pair and I want to know what is the probability the sum is at least 9 given that you know one of the dice is a 6. So let's set up our different events here. Let's call A the event that the sum is at least 9. Let's call B the event a 6 is rolled on one of the dice at least. And then A intersect B would be the sum is greater than or equal to 9 and there's a 6 involved. So let's start with A. If the sum was greater than or equal to 9, I'd be looking at these 10 rolls right here. So the probability of A would be 10 out of 36. Secondly, B is the event that a 6 is rolled. So which rolls have 6s in them? Well, it would be these and these. There's exactly 11 rolls that have a 6 in them. So the probability of B is 11 over 36. And finally, which rolls have a sum of at least 9 and have a 6 in them? Well, those rolls would be there, 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 there. So there's exactly 1, 2, 3, 4, 5, 6, 7 rolls that have a sum of at least 9 and have a 6 in them. So the probability of the intersection would be 7 out of 36. So here's the question. You saw a 6 land. You don't know if it was the first or the second die, but you saw a 6 land. That means my sample space has been reduced to just these 11 rolls. Those are the only ones that are possible. None of these rolls are longer possible. And of those 11 rolls, how many of them have a sum of at least 9? Well, we see 7. So the probability of this problem is going to simply be 7 over 11. Now, that's not intuitively obvious, so we're going to create and establish a formula for that. Now, to summarize the dice roll problem, we want to determine what is the probability of an event occurring given that another one has occurred. And we say the probability of A given B has occurred, and we write it like this. The probability of A, vertical bar, B. Now, if B has occurred, that means I go from a large sample space to a sample space that consists only of B. That means the probability of B is going to be my denominator because that's where the sample space comes from. Now, if that's the case, then if I said, what's the probability of A occurring given B has occurred, then I'm looking for the part of A that is in B, but that's just the intersection. So that would mean this numerator is the probability of A intersect B. Now, if I go back to the last example with the dice, the probability of the intersection, that was 7 over 36, and the probability of my reduced sample space was 11 over 36, and you notice that is our final answer of 7 over 11, as we had in the last problem. So in the general, this gives us the conditional probability, which would mean we need to know these two in order to calculate this one here. Now that we've established this formula, if I want to solve for the intersection, that means the intersection is always going to be the conditional probability times the probability of B. Now, we want to define something here. We're going to say that A and B are independent events if the probability of A given B has occurred is simply the probability of A. Meaning, having B occur has no effect on whether A occurs or not. It's going to occur at the same rate otherwise. Now, if A and B are independent events, then if I go back to this formula, that would imply that the probability of the intersection is simply the product of the probabilities. In general, you do not multiply probabilities to get an intersection. You only do that if the events themselves are independent. Now let's look at a simple example. I'm going to flip a fair coin 10 times in a row, and I want to know what's the probability of getting 10 consecutive tails. Well, we know that's just simply going to be a half to the 10th power, which is 1 over 1,024. It's not very likely. Now, you walk into the game a little bit late. I've already flipped 9 consecutive tails. Now I'm going to flip it one more time. So the question is, does the coin remember that it's landed tails 9 times in a row, or does this start over each time I flip it? Well, you know the answer is it starts over each time because each flip will be independent. No prior flip will affect this flip. So if I said, what's the probability of 10 consecutive tails knowing I've already flipped 9 in a row, that probability is simply 1/2 because I only have to do it one more time. Now finally, I want to know what's the probability of 10 consecutive tails if somewhere in the first 9 flips I have a head. Well, I can't get 10 consecutive tails if I have a head in there, so that probability would simply be 0. So the conditional probability on the last two had a great effect on the final answer. Now let's look at another example. We know that 70% of San Diegans like to go to the beach, and 60% of San Diegans like to watch football. 85% of San Diegans either go to the beach or watch football, and that could also be both. There's 2 events here going on. There's the people that go to the beach, let's call that event B. There's the people who watch football, let's call that event F. Are the events B and F independent of each other? Well, we have enough information to make that conclusion. So let's set it up this way. We know that the probability of the union is the sum of the probabilities minus the probability of the intersection. So that means if I simply swap roles here, then the probability of the intersection is equal to the sum of the probabilities minus the probability of the union. So if I plug in the numbers, this would be 0.7 plus 0.6 minus 0.85, which would be 0.45. The probability of the intersection is 0.45. But we showed earlier, to be independent, the probability of the product, the product of the probabilities, which in this case is 0.7 times 0.6, that does not equal 0.45. So since these are not equal, we would say these events are not independent of each other, meaning they are dependent. Going to the beach does influence the probability of watching football or vice versa.